Physical AI takes functional safety cues from automotive. The automotive industry has established safety standards, but rules concerning safety-critical physical AI are still evolving as more robots work alongside humans. Robots are becoming smarter, more capable, and more pervasive, setting the stage for a wild new round of growth that will touch nearly every part of the semiconductor and software industries for decades to come. Robots are the robots are the echo of physical AI, a broad segment of each AI system that interacts with the world through artificial intelligence and sensors. This includes everything from the humanoid robot to faceless industry robotics, robot dogs, drones, and increasingly autonomous vehicles. In the future, robots will work alongside humans, whether at work, at home, or in a healthcare setting, a companion or assistance. Until recently, industry robots had large safety zones around them so they could not accidentally harm humans. That's starting to change. Better AI models, machine learning, wireless protocols, and sensor fusion mean robots are now capable of working in a close proximity to people, but mistakes can still happen, just as autonomous vehicles occasionally mislead traffic conditions and cause accidents. So the potential for the accident exists if physical AI system goes completely unchecked, said Matthew Graham, Senior Group Director, Verification Software Product Management at Cadence. This is one of the reasons I don't think we were on the precipice of the AI completely replacing the human in the loop. AI is where the value is today and where the productivity gains will be made. But at the end of the day, in terms of autonomous vehicles, autonomous robots, and autonomous industrial, including robots, drones, and so on, to achieve the requirement certification, you have to be able to prove the accessor as well it's a two, who, they say, and you will, that you have well suitably verified and certified the system is safety and the is still has a human signing off on it. Tesla, Robotaxi, and Waymo's self-driving cars are evident that autonomous physical AI is possible. However, drones, robots will have different aspects, such as degrees of freedom, failure modes, and power budget, as compared to automotive systems. Cytologist Vallegaltalati, Principal Security Analyst at Keysight EDA. The regulatory maturity between the automotive and the drones robot is different. It is more defined for cars and not as much for robots. This needs to be addressed. Engineers must determine where the physical AI physical sits on the spectrum from vehicle to robot vacuum cleaner and adopt the matching safety standards. It's been chartered by us to go through the industry to find out and answer exactly the question, where is the partitioning happening for functional safety? Said Anna White, Division President for Power and Sensor Systems at Infineon Technologies. Is it needed? And if it is needed, which element of a robot, humanoid, will need to be meet functional safety regulation? Is it just a microcontroller? Does it go all the way into the power stage? For example, these are the topics and we are now working through openly. What I see in Asia is more speed. They are not waiting for the functional safety. They are just building what they can get and getting it out there to demonstration or to prove them they can do this technology. I really, it's no brainer because if these robots or humanoids has any interaction against the humans, then you're gonna have to have functional safety. The question for us are how much and where you need functional safety. It's a little bit like with vehicle today. There are elements that adhere to functional safety, but do you need functional safety for your radio or your cockpit, for the speed meter your display? As robotics are increasingly interfacing with humans, the root of functional safety is looking at the worst case scenario that can happen. You peel back from there and develop the components and systems based on where you see the safety threshold is, said Paula Jones, Segment Director, Mobility, ADAS, Strategy, Marketing in Infineon. In the past, there were robots in factories, and well, they were working with either close off to humans or extreme safety measures were put in place. Now we see that there are more robot-human interactions. Functional safety standards are migrating to the robotics industry, and the same with the cybersecurity. Automotive security and safety organization (SSOs) are at the forefront of standardizing tamper-resistant security features of automotive microelectronics. Everyone, including a large portion of U.S. defense microelectronic providers, is following their lead, said Scott Best, Senior Director for Silicon Security Product at Rambus. The regions are varied, but they all boil down to human safety. As a security flaw in an automotive safety system presents an immediate and obvious risk of physical harm. Importantly, the progress being made by automotive SSOs translates directly to robotic or physical AI systems. A self-driving car is a robot with wheels, after all, and a drone with a self-piloting expert system is just a robot that flies. Automotive and robotics standards. There is a lot of energy and similarity between robotics and adjacent vectors in terms of functional safety and the use of AI. You could have a standard paralysis, as in which standards should look at, said Andrew Johnston, engineering and technology leaders, system and functional safety engineering specialist, and imagination technologies. They are saying similar but different things. Robotic standards are evolving generally, underpinned by de facto functional safety standard ICE 61508, but there are adjacent standards for machinery and all other autonomous systems, including vehicles. Today, some standards explicitly include the use of AI for high-integrity functions. Emergent standards are now trying to find a way to, with credibility, use AI as part of a safety assurance case, whether that's in the design and development life cycle or as the technology within the product itself, or both. Just noted. As technology is evolving concerning ML, and there is a growing understanding of the benefit of ML for certain applications, the standards have to evolve too. Sometimes it's a little bit of a chicken and egg scenario. The need for redundancy for functional safety and conforming to standards like ISO 26262 is impacting the design of a physical AI. Our customers are driving us to ensure that our tooling is certified, that we can provide certified flows, and that they can use those flows to certify their devices, Cadence Graham said. Whether drone, vehicle, or robot, physical AI can face harsh conditions from heat, cold, weather conditions, moisture, and environmental toxins, and this is where will be a crossover with the optional functional safety and reliability. Either S will be the first for safety, and AEC Q100 for grade 2 to operate reliably in an ambient temperature range of -40 degree to plus 105 degree in Celsius, said HSR Executive Director, Product Manager, Mobile, Automotive and Consumer IP at Synopsys. These are things that some of the robotics developers are going after. Some of them are in factories. Some of them are going after markets that are no-brainers. That market will adapt immediately, like helping elderly people and dangerous jobs, such as cleaning the window outside a skyscraper. Example of a standard is global progress for robotics. IS 13482 personal care robots, IS 13849 robot safety for machinery, IS 10218 industry robots, including autonomous mobile robots, ANSI LEA R15.08 autonomous mobile robots. Regional derivative like JISB 8445 in Japan and CSA G434 in Canada, and IEEE Robotics and Automation Society RAS Technical Committee on Safety, Security, and Elastic Robotics SSRR. So emerging standards in research, UL 4600, a key framework for autonomous product safety that emphasizes system-level hazard assessment. IEC 61508 focuses on functional safety, electrical and electronic systems, offering insight for humanoid sensor and control system. BSI 8611 provided a ethical guideline for robot safety in public spaces, which is critical for humanoid robots operating outside industry environments. These standards show the robotics industry is considering safety, but it's unclear how widely they will be adopted globally. The standardization and taking care of system level and application are being discussed at least, Sarah said. I don't know about the implementation itself, but the concern I have is more as a consumer, as a human being, that we are rushing with AI innovation. While regulations are not there worldwide, sometimes professors A, B, and C are running. Hey, what are you going to do? Guys, we have to make sure everybody is following the same rule. And for this paper, we advance technology and assuming that everybody is behaving well. Figure 1. Innovation in robotics. A mix of robotics and automotive standard through synopsis. So, physical AI, simulation, and real-world safety measures for software-defined vehicles. For software-defined vehicle and physical AI system, safety needs to be considered from simulation through to prototype. For the software-defined methodology to work, you start with something that's purely virtual. So David Pritz, Vice President of Hybrid Physical and Virtual System, Automotive and Military Aero and Defense EDA. It has to be valuable. You've got to get hours. After a minute, where the software teams and hardware teams are churning quickly. They are trying to all these different things. They were trying to iterate to get to the point where they can prove success in passing some of these hardware requirements. That's pure virtual, and that's a lowest level of fidelity, but it's enough fidelity to reach that first gate. Then we have a higher level of fidelity, where we start to say we are modeling the behavior of the hardware. We are modeling the hardware itself, down at the gate level, at the signal level, and yet we are learning proposed production software. Hybrid is halfway between virtual and physical. At the end of the process comes something truly physical, a prototype. It could be plane or rocket ship, of the car and freights. The reason you need to that is you've done millions of simulation runs virtually. You've done millions of inhabited. You're passing all the requirements, but you still need to verify that you get the same result in the physical and vehicle and in the list in the worst case, and the abnormal case of the all of the call those simulations to gain confidence, and you're not being fooled by some simulation glitch. That's a whole spectrum of the fidelity that's needed to be successful in this project. The video applies is a Halo safety initiative for automotive vehicles to robotics, which includes the simulation. The safety element of this is something that has to be done across the whole stack from top to bottom, from all of the software down to the chip and the system level. Sator Lubaledian, Vice President of the Omniverse and Simulation Technology at NVIDIA. There's a lot of overlap between both the hardware and software, between what we do in AV and the robotic world, and we are applying it there. This is a very, very large effort that has many facets, and functional safety has many best practices, guidelines, and safeguards in terms of evaluating and testing these AIs. A big portion of that is testing extensively and simulation before deploying into the real world. So that's why it's so critical that we build physically accurate simulators that match the world as closely as possible. We can test these robots and fleets of robots for millions of billions of hours of operation in diverse environments before we put them out in the physical world and give them a physical body. Whether in automotive or robotics applications, physics AI, situational environmental awareness can be through the training. There's a limit. You can train a vehicle control with lots of face value, good data about the road condition, road signage, and temperature variation, said Imagination Johnston. You can use a number of sensory inputs to do that. But as a human, when we are old enough to get behind the wheel of a car. We have been brought up in a certain environment with certain values, with a certain inherent moral and ethical understanding and social responsibility. That's real hard things to train a computer in. By the time you drive, you've spent 16 or 17 years on this planet, and you've been in lots of interesting social environment to learn about how people interact, learn about general risk management or social responsibility. Some of that's good, and some of it's bad. How to train a machine learning models to do that on the top of just operational or environmental situational awareness. If you try to model a human, your input data, if you could even quantify it, would be far broader and far more detailed. That's why I prefer to use the term machine learning, because a lot of these models are not intelligence. As you love to have bounced off industrial settings and enter the world, more types of safety control are emerging. The safety requirements as we are inventing a new technology are high, but not as high as they will be eventually. When we get to billions of humanoids that are going to be amongst us, working with us in a collaborative manner, said Deepu Tala, Vice President and General Manager of Robotics and Edge AI at NVIDIA. Speaking of October Tech, there's a lot of work that needs to be done in safety, but the other cool thing is that we can apply safety not only inside on the robot, and we have an air traffic control scenario. Every plane is autonomous with a pilot or using a pilot, but they can't do the job in themselves without an air traffic controller. For example, in China, one company is navigating drone deliveries. They've got the added complex of altitude, which flight path they are delivering in urban areas set infinite wide or something by drone, and it drops in into a location, and they have to figure out which of the flight paths take off. They get approval from a local agency that a drone could fly this flight path. This is next level. Eventually, vehicles will be able to detect if the load is sand, snow, mud, or another type of surface, and adjust their behavior accordingly, he noted. Boosting physical AI safety, precise GPU, and protocols like ultra-wideband (UWB) wireless can help boost safety for physical AI on the move in our own facilities. At back-end facilities and test, there is a very precise GPU notation within the facility to know exactly at any moment where the robot is. Said wide, we have the ability to track everything with very close accuracy within the spectrum that we're going to setting up some kind of base station. It's a bit like air traffic control, although we know exactly where everything's going. Companies can deploy safety by leveraging all the sensors in a factory or manufacturing facility and using that information. You can see what's happening on a factory floor as well as autonomous or semi-autonomous robot and even humanoids at the point, says Tala. There's a lot of work that must be drawn in the area of safety, both in the robot and outside. Figure 2. Silicon needed for the humanoid source TSMC. Architectural crossover between the automotive physical AI. From an architectural perspective, the automotive world is moving from a distributed architecture with ECUs all over the centralized system, and a physical AI looks set to follow. There are many benefits to that, said Infineon Jones. One of the key benefits is that automotive OEMs and tiers automotive suppliers can do software update over the air. They can reduce the size of modules and enables a lot of other features, including AI. We see the same kind of activity in robotics, where there's a centralized computer and there's a smaller zones in the robot, like the the arm zone. Figure 3. Zonal compute in a robot development through Infineon. The like arm zone. The others agree that a physical AI will follow a similar trend to automotive. You will see genre-like architecture in a physical AI because at the end of the day, what's the difference between a robot and a car? They both move. Said of Michael Swinsky, Mitchell Swinsky, Chief Marketing Officer at Arthurs. They both need to be mission-critical systems. They just move differently. We are thinking that a whole industry 4.0 with physical AI and the evolution has a lot more to do with autonomous and autonomy that is actually coming from and driven primarily by the car. So the automotive industry is probably best proxy. There's communication and there's enterprise and there's other functions. But the car is the proxy industry in that regard. Further weaker robotics and physical AI system can deploy edge AI processors designed for real-time functional and reliability within the built-in security. You can have a vision-based system on a manufacturing line or robotics or other things where you need a highly reliable execution path, but you still want to be able to execute today's modern AI algorithms or models, said John Well, Vice President General Manager for IoT and Edge AI Processor Business at Synaptics. The cherry on the top is succeeding with a high degree of security. For vision, AI connected to LLMs and the system might be connected to internet or a data center, which brings its own risk at a model that is no longer a tightly coupled embedded model where you put in an input and you get an output and it's now a model that makes a decision on the fly. So well, security is paramount. China's speed. So far, China is leading the way when it comes to robot adoption. The train have left the station in China. When it comes to robotics, opinion, why? Noted. Further, China's automotive trend could signal what the next full automotive and physical AI development. The automotive market growing the fastest right now in Asia, specifically in China. China's automotive market is a lot more consumerized than the rest of the world, which is struggling a bit or slowing, said Satish Ganesan, Senior Vice President and Chief Strategy Officer as a statistics. There's going to be a convergence of the consumerized automotive. There's a lot of more traction in EVs and autonomous driving vehicles, and we'll see that the things can come to pass faster. It's not going to be the same as before, when they were bogged down by regulations. There will be aspect of it, learning of vehicles, autonomous driving. The things will be regulated, and the subtle aspect of the will be less so. For implementing all of this, I do know that automotive companies are using AI for development. Conclusion. Overall, it is a big moment for physical AI, enabled by large and small language models, multimodal sensors, and simulation technology development, along with the labor shortage and massively industrialization of regions such as the United States and Europe. And if you combine all three things, we have entered the golden age of robotics and physics, AI, and the next 10-year trajectory of how we can solve some of these problems. Divya Starla said, almost nothing has been solved today, even though the automation has existed for 50 plus years. In the last years, even in AI, in the form of deep learning and some transformation and vision transformer, much of the AI that's been deployed today is extremely brittle and very specific purpose. We need to get to a general purpose. Okay, today I read this article, Physical AI that takes functional safety cues from automotive. Thank you for your time. See you next time.